The images you are seeing are not science fiction, but a model of a city on the moon that China is planning to build, a goal that NASA and SpaceX have not yet made their main focus. The paradox is that the moon is one of the most hostile environments humans have ever faced. There is no air to breathe, no magnetic shield for protection, and cosmic radiation is a constant and deadly threat. In a place like this, survival alone is already a challenge, let alone building an entire city. Yet China continues to move forward. Instead of sending humans first, it sends robots ahead to learn, to test, and to accept failure. Only when infrastructure and life support systems are fully prepared do humans appear. In this video, we will analyze that strategy and take a first look at the foundations of a lunar city that is slowly taking shape. The moon is often described as quiet and empty, but from a scientific point of view, it is one of the most extreme environments humans have ever tried to operate in. Unlike Earth, the moon has no atmosphere, which means there is no air, no pressure, and no natural protection of any kind. This single fact creates multiple layers of danger, because an atmosphere does more than allow breathing. It regulates temperature, absorbs radiation, and burns up incoming debris before it reaches the surface. On the moon, none of these systems exist. When sunlight hits the lunar surface, heat builds up directly in the soil and rock, pushing surface temperatures above 120 degrees Celsius. When the sun sets, that heat is lost just as quickly, and temperatures fall below -130 degrees Celsius. Because the moon rotates slowly, this is not a short cycle. Each location experiences about 14 days of continuous daylight, followed by 14 days of darkness. For any mechanical system, structure, or biological process, this creates severe stress over long periods. Materials expand, contract, weaken, and eventually fail under these repeated extremes. Radiation presents an even more serious challenge. Earth is protected by a magnetic field generated by its molten core, which deflects most solar and cosmic radiation. The moon has no global magnetic shield, so high-energy particles strike the surface constantly. Over time, this radiation damages human tissue, disrupts electronics, and degrades construction materials at the molecular level. Shielding against radiation is not optional, but essential for survival. Then there is the problem of impacts from space. Micrometeorites hit the moon every day at very high speed because there is no atmosphere to slow them down. Even particles smaller than a grain of sand can puncture equipment or compromise sealed habitats. The moon's surface is covered in craters as evidence of this continuous bombardment. These conditions explain why earlier missions treated the moon as a place to visit, not to stay. During the NASA Apollo program, astronauts remained on the surface for only a few days. Those missions were carefully timed, tightly controlled, and designed to minimize exposure. There was no realistic way to extend them into long-term habitation with the technology of the time. Short stays reduced risk, but they also revealed an important limitation. Human endurance alone cannot overcome the lunar environment. Any attempt at permanent presence must rely on engineering, not adaptation. Life on the moon cannot evolve naturally or adjust slowly. Every condition that Earth provides for free must be recreated artificially and maintained without interruption. This turns survival into a systems problem rather than a human challenge. Air, temperature control, radiation shielding, power supply, and structural integrity must all function perfectly at the same time. A failure in any one system can quickly become fatal. This reality forces a different way of thinking about exploration. Instead of sending people first and solving problems later, the environment must be fully understood and controlled in advance. Mistakes need to happen without human lives at risk. Testing must be slow, repetitive, and sometimes destructive. Only after the moon's dangers are measured and managed does long-term presence become possible. This understanding leads directly to the next phase of China's approach, where theory met reality through a real experiment that failed under lunar conditions and revealed exactly how unforgiving the moon truly is. The extreme conditions described in the previous section were not just theoretical risks, because China tested them directly on the lunar surface and the results were unforgiving. In 2019, China launched the Chang'e 4 mission to the far side of the moon, a region never visited by any spacecraft before. Alongside scientific instruments and mobility systems, the mission carried a small but ambitious biological test known as the lunar microecosystem. The goal of this experiment was not symbolic, but practical. Scientists wanted to understand whether a sealed life system could survive on the moon when supplied with air, water, and nutrients. Inside the container were cotton seeds, potato seeds, fruit fly eggs, and yeast, chosen to represent a simple but complete biological cycle. If life could survive here, even briefly, it would offer critical data for future habitation concepts. At first, the experiment appeared successful. Shortly after landing, the cotton seeds germinated and sprouted, marking the first time plant life had ever grown on the moon. This moment was widely reported as a breakthrough, but from an engineering perspective, it was only the beginning of the test. The real challenge was never growth under ideal conditions, but survival during the lunar night. As the sun set, surface temperatures began to fall rapidly. Despite insulation and careful thermal design, the internal temperature of the container dropped beyond survivable limits. Within days, all biological activity inside the microecosystem stopped completely. Nothing survived. This failure was not unexpected, but it was deeply informative. It confirmed that surface-level protection is insufficient for long-term biological systems on the moon. Even sealed containers with controlled air and water cannot withstand the thermal extremes without far more advanced shielding. More importantly, it demonstrated that temperature instability is as lethal as radiation. Radiation often receives more attention in lunar planning, but the microecosystem showed that heat loss alone can end a system just as effectively. From a scientific standpoint, this failure validated decades of assumptions about the lunar environment. Models predicting rapid heat loss during the 14-day night were proven correct. Estimates about the limits of passive insulation were confirmed under real conditions. What simulations suggested, the moon enforced. Unlike a laboratory failure, this result carried unique value because it occurred in the actual environment future humans must face. China did not attempt to downplay or ignore the outcome. Instead, the failure triggered a clear shift in design philosophy. The lesson was simple but severe. Any system exposed directly to the lunar surface will eventually fail. Life support cannot rely on thin walls, shallow shielding, or temporary solutions. Survival requires separation from the surface environment itself. This conclusion influenced every stage of China's subsequent planning. Rather than asking how humans could endure the moon, engineers began asking how structures could isolate humans from it entirely. Biology became a dependent variable, not the driving force. Engineering came first. Another key insight emerged from the experiment. Short-term success is not meaningful in lunar conditions. A system that functions for hours or days proves almost nothing. Only systems that operate across multiple day-night cycles can be considered viable. This reframed the definition of progress. Instead of celebrating early results, China focused on endurance and repeatability. Failure was no longer seen as a setback, but as data. Each breakdown narrowed the design space and removed unrealistic assumptions. The lunar microecosystem did not show that life is possible on the moon. It showed exactly why life is not possible without deep structural intervention. That distinction is critical. The moon does not gradually reveal its dangers. It applies them immediately and without compromise. For any nation attempting permanent presence, ignoring these lessons would be catastrophic. China's response to this failure reveals an important strategic difference. Rather than rushing toward crewed missions, the program doubled down on robotic testing. Every system would be stressed, exposed, and allowed to fail before humans became involved. The moon would not be treated as a destination for heroism, but as a hostile system that must be understood in detail. This approach sets the foundation for the next stage of the plan, where robots are no longer experimental tools, but the primary agents responsible for mapping, building, and preparing the lunar environment long before any human footprint appears. The collapse of the lunar microecosystem experiment made one conclusion unavoidable, because the moon does not allow gradual learning through human presence, and any serious plan must remove uncertainty before lives are placed at risk. From that moment, China's lunar program shifted from exploration driven by milestones to a structured engineering sequence designed to reduce unknowns step by step. Instead of aiming for a dramatic human landing as the first objective, the strategy was reorganized into 3 connected phases that build on one another with clear technical purpose. The first phase is reconnaissance, and this stage is not about discovery in the romantic sense, but about measurement, verification, and exposure of weaknesses. Robotic orbiters survey the surface from above, mapping elevation, slope stability, and temperature behavior across full lunar cycles, while landers and rovers collect ground-level data that satellites alone cannot provide. These machines analyze soil composition, dust behavior, radiation intensity, and subsurface structure, producing data that directly influences where construction is even possible. The Chang'e missions serve this role with increasing complexity, because each mission adds another layer of environmental understanding rather than repeating the same task. Chang'e 4 proved that long-duration robotic operations could survive on the far side of the moon, while Chang'e 5 and Chang'e 6 returned physical samples that allowed engineers to test lunar material under Earth laboratory conditions. Chang'e 7 extends this process by focusing on the lunar South Pole, a region defined by extreme lighting conditions and potential water ice, which makes it both promising and dangerous. This reconnaissance phase is deliberately slow because its goal is not speed, but certainty, and uncertainty is the greatest threat to any permanent system. Once enough variables are constrained, the program moves into the second phase, construction, which represents a fundamental break from earlier lunar efforts. In this stage, robots are no longer observers but builders, operating autonomously to prepare terrain, assemble structures, and test infrastructure without direct human supervision. Landing pads are stabilized to control dust, structural shells are assembled to test shielding performance, and power systems are deployed to evaluate reliability across long lunar nights. These activities are not demonstrations meant to impress an audience, but stress tests designed to push systems until failure occurs. When a structure cracks, when power drops, or when thermal control fails, engineers gain information that could never be obtained from simulations alone. This willingness to allow failure is intentional because failures during robotic construction are survivable, while the same failures during human missions would be catastrophic. Only systems that remain functional across repeated lunar cycles are considered viable for long-term use. The third phase, habitation, is delayed by design, because in this framework, humans are not pioneers but the final payload delivered into a prepared environment. By the time astronauts arrive, Shelters are already pressurized, energy production is stable, communication networks are active, and life support systems have been tested without interruption. Human presence becomes an extension of an existing system rather than the starting point of one. This approach minimizes the need for improvisation, which is often celebrated in exploration history but represents unacceptable risk in an environment as unforgiving as the Moon. Compared to earlier models of space exploration, where human endurance compensated for technical limits, this strategy places engineering reliability above symbolic achievement. A city cannot emerge from short visits or temporary camps because permanence requires maintenance, scalability, and predictable performance over years rather than days. Robots are uniquely suited to establish this foundation because they operate without concern for radiation exposure, temperature extremes, or extended darkness, and they can repeat tasks with precision until acceptable results are achieved. Through this three-phase blueprint, the Moon is gradually transformed from an unknown hazard into a managed construction site governed by data rather than ambition. With reconnaissance reducing uncertainty and robotic construction proving feasibility, the next challenge becomes unavoidable, because even the most carefully built systems cannot succeed if they rely entirely on materials transported from Earth. Once China's three-phase strategy is understood, the next problem becomes clear, because no lunar city can exist if every wall, road, and shelter must be launched from Earth. The cost of lifting mass out of Earth's gravity well is enormous, and even the most powerful rockets can only deliver limited payloads to the Moon. Every kilogram sent into lunar orbit requires fuel, time, and repeated launches, which quickly turns large-scale construction into an unsustainable equation. For a permanent settlement, this approach would collapse under its own weight long before the first building is finished. This reality forces a different solution, one that space agencies have discussed for decades but rarely tested in practice. That solution is in situ resource utilization, often shortened to ISRU, which means using materials already available on the Moon instead of importing them from Earth. For China, ISRU is not an optional upgrade or a future improvement. It is the only path that makes a lunar city physically and economically possible. The focus of this strategy is the lunar regolith, the loose layer of dust and crushed rock that covers the Moon's surface. At first glance, regolith looks useless, but chemically it contains elements that can be transformed into solid construction material under the right conditions. This idea moves from theory to reality with the Chang'e 8 mission, which is designed to test whether lunar soil can be converted into usable building blocks. Autonomous machines collect regolith, compress it into molds, and heat it to extremely high temperatures, effectively sintering the material into solid bricks. These bricks are not meant to resemble houses on Earth, but to serve specific structural roles that reduce risk and increase stability. Thick regolith bricks can be stacked to form radiation-shielding walls that block harmful particles from space. They can also be laid flat to create hardened roads and landing pads, which reduce dust clouds during spacecraft landings and protect nearby equipment. By producing these materials directly on the Moon, the need to transport massive shielding from Earth is removed. However, this method introduces an important limitation that cannot be ignored. Rectangular and rigid brick structures are poorly suited for holding internal air pressure. On the Moon, every living space must contain its own atmosphere, and pressure constantly pushes outward against the walls. Flat surfaces and sharp corners concentrate stress, increasing the chance of structural failure over time. This is why pressure vessels on Earth, such as fuel tanks and underwater habitats, are almost always round. The physics does not change simply because the structure is built on the Moon. As a result, regolith bricks are excellent for protection and infrastructure, but unsuitable as primary living spaces on their own. This limitation forces a separation between protective architecture and habitable architecture. Shielding, roads, and external barriers can be constructed from solid lunar bricks, while human living areas require shapes that naturally distribute stress. Understanding this boundary prevents dangerous assumptions and pushes designers toward more realistic solutions. It also explains why China does not rely on a single construction method, but instead combines multiple approaches depending on function. ISRU solves the mass problem, but it does not eliminate physical laws. Every design must respect pressure, temperature, and material behavior under lunar conditions. Ignoring these limits would turn a city into a fragile experiment rather than a durable system. By acknowledging what regolith bricks can and cannot do, China avoids repeating the mistakes of earlier space concepts that prioritized imagination over engineering. This careful balance between ambition and constraint sets the stage for the next development, where new architectural forms and stable energy sources become essential for turning infrastructure into a city that never sleeps. Once the limits of brick-based construction are clear, the problem of true habitation comes into focus, because a city cannot exist without spaces that safely hold air, people, and life support systems for years at a time. This is where China's approach moves beyond simple shielding and enters the realm of structural engineering designed specifically for an airless world. The answer is not a traditional building, but a new form of habitat often referred to as the moonpot, a structure shaped by physics rather than aesthetics. Instead of straight walls and sharp corners, the moonpot uses a rounded form inspired by one of nature's strongest designs, the eggshell. This curved geometry spreads internal pressure evenly across the surface, reducing stress points that would otherwise weaken the structure over time. The habitat is built using a layered system with an outer shell, an inner shell, and a ribbed internal structure that distributes loads throughout the body. This design allows the habitat to remain pressurized without relying on heavy metal pressure vessels brought from Earth. Construction begins with robots laying down a thick foundation made from processed lunar soil, which anchors the structure to the surface and absorbs vibrations from moonquakes. Moonquakes may sound rare, but seismic activity on the moon occurs regularly and can last much longer than earthquakes on Earth due to the moon's rigid interior. By printing the habitat directly onto a stable base, the structure becomes part of the terrain rather than something simply placed on top of it. Low lunar gravity further improves this approach because reduced weight lowers stress on materials and makes taller structures possible without the risk seen on Earth. Movement inside these habitats also becomes more efficient, allowing vertical layouts that would be impractical in stronger gravity. However, architecture alone cannot sustain a city because every system depends on energy, and the moon presents one of the most difficult power environments imaginable. Solar energy works well during the lunar day, but it becomes useless during the 14 days of continuous darkness that follow. Batteries capable of storing enough power for that duration would be massive, heavy, and prone to degradation under radiation. For a settlement that must operate without interruption, solar power alone is not enough. This reality leads to a solution that may sound extreme, but is scientifically practical. Nuclear energy provides dense continuous power regardless of sunlight, temperature, or surface conditions. China's decision to pursue nuclear power on the moon reflects a focus on reliability rather than public perception. In partnership with Russia, China plans to deploy a nuclear power system capable of supporting construction, life support, communications, and automation through long lunar nights. Russia's experience through its state company Rosatom includes building reactors for remote and hostile environments, including floating nuclear plants in the Arctic. Compared to Earth, the moon offers advantages for nuclear systems because cooling can be achieved by placing reactors in permanent shadow or beneath the surface. Without an atmosphere, heat dissipation behaves differently, and extreme cold becomes an asset rather than a problem. Concerns about environmental contamination also carry less weight, since the lunar surface is already exposed to constant cosmic radiation. With stable energy in place, the nature of the settlement changes fundamentally. The base is no longer a fragile outpost dependent on timing and sunlight. It becomes an industrial system that operates continuously, expanding infrastructure, repairing damage, and supporting human activity without pause. Automation systems can run through the night, 3D printers can continue building, and life support remains stable regardless of external conditions. At this stage, the concept of a city becomes realistic because permanence depends on uninterrupted function rather than occasional success. Moonpot habitats provide safe living space, while nuclear power ensures that no critical system goes dark. Together, they form the backbone of a settlement designed to endure rather than simply survive. With architecture and energy solved, attention naturally shifts to the question of location, because even the strongest structures benefit from natural protection offered by the moon itself. After addressing construction methods and energy supply, China's lunar strategy reaches its final stage, because even the most advanced surface habitats still face unavoidable long-term risks. Radiation exposure, constant micrometeorite impacts, and extreme temperature swings make surface living increasingly fragile as time passes. For a settlement meant to last decades, protection cannot rely only on artificial walls and shields. The most logical solution is already built into the moon itself. Beneath the lunar surface lie vast lava tubes created billions of years ago when molten lava flowed underground and later drained away, leaving behind enormous hollow tunnels. Some of these underground spaces are wide enough to contain entire neighborhoods, offering a scale that surface construction struggles to achieve safely. The thick rock above lava tubes provides natural radiation shielding that far exceeds what human-made structures can deliver. That same rock layer also blocks micrometeorites entirely, removing one of the most unpredictable dangers of life on the moon. Inside these caverns, temperatures remain far more stable than on the surface, avoiding the brutal 14-day cycle of extreme heat and cold. Instead of constantly fighting the environment, underground habitats allow engineers to work with it. China understands this advantage, which is why subsurface exploration is a core part of its lunar plan. The Chang'e 7 mission is designed to scan the lunar South Pole using ground-penetrating radar, mapping what lies beneath the surface and identifying lava tubes that could support future development. Surface habitats and moonpot structures still matter, but they are viewed as transitional steps rather than the final destination. They support early operations, test life support systems, and enable construction while underground sites are prepared. All of this activity centers on the lunar South Pole, where permanently shadowed craters hold ancient water ice. Water supports human survival and can be converted into oxygen and fuel, reducing dependence on Earth. While NASA targets the same region, China's strength lies in preparation, because robots establish infrastructure long before people arrive. Through lava tubes and polar resources, China's lunar city moves from vision to permanence, transforming the moon into a place designed for long-term human life rather than short visits. What China is building on the moon is not a race to plant flags or win headlines, but a long game built on engineering, patience, and control of a hostile environment. Instead of sending people first, China sends robots to fail, learn, and prepare, turning the moon itself into shelter, infrastructure, and fuel. From surface construction and nuclear power to underground lava tubes and polar water ice, every step is designed for permanence, not spectacle. If this strategy succeeds, the moon will no longer be a place humans briefly visit. It will become the first city beyond Earth, built not by courage alone, but by preparation that leaves nothing to chance.